Our goal today is to learn something called u-substitution. And what u-substitution will allow us to do is it's going to allow us to find indefinite integrals and undo the chain rule. So if you think about that example that we saw at the end of class last time, we had cosine of 5x. When we tried to anti-differentiate this or integrate this, we thought that maybe sine of 5x would be the answer, but when we checked our answer, we saw that wasn't quite right because of this 5x inside, so we really needed a 1/5 out front here. And that kind of came from a guess and check. What we want to do today is we want to learn how we can figure that out without guessing and checking. And what you notice here is different about this example is that the original function really has a chain rule going on. If I try and take the derivative of sine of 5x, I need the chain rule. So our goal is how do we undo the chain rule? And so let's just write down the chain rule. You might have different ways of writing it, but the way that I wrote the chain rule is the derivative of f of g of x is f prime of g of x times g prime of x, remembering the chain rule undoes, or the chain rule works with composition of functions. So if I'm anti-differentiating things, if I integrate f prime of g of x times g prime of x dx, then the function whose derivative is this is f of g of x. So this is what I would get. So there we go, we've undone the chain rule, but that's not very helpful. So we need to know, how do we make this work for us? So the trick here is, if you notice, we're going to be integrating things of this form. And the key thing to notice here is that in this expression, we have a function g of x that lives inside something else, and g prime lives in our integral as well. So what we're going to do is we're going to try and identify functions where the original function is in our expression and its derivative is in our expression, and then we're going to try and do something with that. So let's do examples, because that's going to be the best way to see this. So if I look at this expression here, I'm looking for my function g, so that g and g prime both live inside my integral. G is probably going to live inside some other function. So let's look at this. What about 1 plus x cubed? If I choose g to be 1 plus x cubed, g prime is 3x squared, which does indeed live in my integral. So it looks like I found g, but now how do I go about doing this? So what we're going to do is, we called this u-substitution for a reason. So we're actually going to, instead of using the variable g, we're going to call this u. So we're going to start out by saying, let's let u be 1 plus x cubed. The hard part of u-substitution is always picking what u is going to be, and we'll talk about how to do that eventually. So now I need the derivative of u. Always start by finding u and then find its derivative. So du dx, we're taking the derivative of u with respect to x, since x is my variable. You can also see, since there's a dx at the end, I'm going to need to worry about that. So its derivative is 3x squared. What I'm going to do now is I'm going to try and write my integral totally in terms of u. And in order to do that, I'm going to say, what is dx equal to, so that I can replace this dx with an expression that has u in it. So if I solve here, I'm going to have du is 3x squared dx. So du over 3x squared is dx. So now I'm going to rewrite this integral in terms of u. So I have the integral. The 3x squared will eventually go away. Okay, so we've got our 3x squared. Then we're going to have a square root of u, and my dx is du over 3x squared. And we want to get rid of all the x's. That's our goal. We want an integral that totally has u in it. So the 3x squareds here nicely cancel out. So we're left with the integral square root of u is u to the 1/2 du. And now, hopefully at this point in time, this is something that we can anti-differentiate, and it is. So this is just u to the 3/2 times 2/3 plus c. And finally, our original integral had x's in it, so we need to replace the u's with their x's. So with this, so we have 2/3, 1 plus x cubed to the 3/2 plus c. So what you noticed here is we had to start out by identifying what u was. That was a function that appeared in my integral and whose derivative also appeared in the integral. Then we found the derivative of u so that we could rewrite the integral totally in terms of u. Once we did that, we're hoping that we have something we can anti-differentiate. And so then we anti-differentiate and plug u back in. So why don't you think about what you would do with this next example? What would you pick u to be? What would du over dx be? And then see if you can rewrite this. Hopefully you've had a chance to think about what you would do for this one, or at least how you would get started. So once again, when we look at this, we're going to pick our u to be oftentimes something that lives inside of another function, and we want to pick u so that its derivative lives in here as well. So if I look at this, I have that x to the fourth, or the 4x cubed, but the derivative of x to the fourth is 4x cubed, so it would be good to pick x to the fourth for my u. And then du over dx is 4x cubed. So if we solve for dx, I'll do this in one step, but you might need more steps. We get du over 4x cubed. So when we rewrite the integral, we have that 4x cubed e to the u, du over 4x cubed. The good thing is the 4x cubes both cancel out, so we're left with the integral of e to the u du. Hopefully this is something we can do now, and we can. The antiderivative of e to the u is e to the u plus c. And now we substitute our u back in, so we have e to the x to the fourth plus c. Remember, you can always check your answer by taking the derivative of this expression. When you take that derivative, you'll need the chain rule, and hopefully you should get back to our original expression. Okay, so you should try this one. What's u gonna be? What's du? So I'm going to pick u here to be 2, or not 2x, x squared plus 3. So notice that when I take the derivative of x squared plus 3, I get 2x. I have an x here, but not a 2. That's okay because the 2 is just a constant. We'll figure out how to deal with that in a minute. Once again, the x squared plus 3 lives inside of another function, so that's why it seems a reasonable choice for u. So my du over dx is just 2x. Solving for dx gives me du over 2x. So my integral is then x sine of u times du over 2x. The x's cancel out. We're still left with that 2 in the denominator, but that's okay. So this piece here is really like 1/2 times du. So I'm going to pull that 1/2 all the way outside of the integral. It's okay if you leave it in there though. So I have 1/2 integral of sine of u du. The antiderivative of sine is negative cosine. So we have negative 1/2 cosine of u plus c. And this gives us negative 1/2 cosine of x squared plus 3 plus c. So when we look at cotangent, it's not obvious that this is a u-substitution, but hopefully you think to rewrite this as cosine of x over sine of x. And there's a lot of things to think about in this problem. So now we need to pick our u. We know the derivative of cosine is sine, negative sine, and that the derivative of sine is cosine. So it seems like I could pick either of these expressions to be my u. But we actually don't want that. What we want to be careful about is that when we get our du is always just supposed to be at the end of the integral. It's not supposed to be inside of another function. It's not supposed to be in the denominator. So remember that du is just telling us, or the du or dx is just telling us x is my variable, u is my variable. And it's really supposed to be ending the parentheses of the integral sign. It's just the thing, the bookends, the integral sign and the dx are the bookends of our integral. So we don't want our du to be in our denominator, which means that we really should pick our u to be sine of x, because otherwise du will end up in the denominator. So then du over dx is cosine of x, which means that dx is du over cosine. So when I rewrite my integral, I have cosine over u times du over cosine. Cosines cancel out. I have the integral of 1 over u du. Antiderivative of 1 over u is ln of the absolute value of u. Don't forget those absolute values. And when we replace our u back in here, we get ln of the absolute value of sine of x plus c. You could anti-differentiate tangent in the same way. So if you want some extra practice, you could try that. And so if you haven't tried this one, try this one before you watch my video here. So I'm going to pick my u to be 4x minus 1. You might think, well, there's not something else, its derivative's not in here, but the derivative of 4x minus 1 is just 4, so we don't really need anything else in here, and that's okay. So we have du over dx is 4, So dx is du over 4. So when I rewrite this integral, I have the cubed root of u times du over 4. Du over 4 is 1/4 du, so I'll pull that 1/4 out. The cube root of u is u to the 1/3. So I have 1/4, I'll have u to the 4/3 times 3/4 out front plus 3. So this gives me 3/16 4x minus 1 to the 4/3 plus c. Okay. If you feel a little rusty about u substitution still, that's okay. We're going to get a lot more practice in class. So just stick in there. It'll get better as you do more practice.